place that we were at last class, we were talking about creating new power series for different types of functions from known power series. And so the main thing here is that we're doing it through either a derivative or an integral. And so we started with our geometric series for the one that we completed on Tuesday. And we discovered that we had to take a couple of derivatives of the geometric series to get to this function g. The drag about this is that the interval of convergence when you differentiate or integrate is ambiguous on the endpoints. If you differentiate or integrate, you have to test the endpoints again. So we had some nice short things that if you had a power series and you multiplied by a power of x, you didn't have to change the interval of convergence. If you did a substitution, you just also substituted into the interval of convergence to get the new one. So that was a lot easier. Dealing with derivatives and integrals, we have this extra thing that we have to test our endpoints. So we just have to remember that. And this is where we were on Tuesday at the end of class. Our goal is to find the power series for G. Power series, remember, is a series of powers. It's a big, long polynomial. And we discovered that, okay, well, we know how to find the power series for f. We haven't done it yet. But once we have that, we are going to use that to get the power series for g. And we saw that if we integrate f, we're getting pretty close to g. So we need to have a little roadmap that tells us how to get to g from doing something to f. So that's what we're trying to establish right now. So what I want to do is isolate the part that is g. So the next step here, I'm going to isolate natural log of 1 plus x squared. So to do that, I'm going to multiply both sides by 2 and subtract off that constant. So I'm multiplying both sides by 2. So we have that. And then subtract off the constant. And when it's subtracted to the other side, technically it becomes a minus c, and you multiply by 2 and it becomes minus 2c, but it's just a constant. So we could just write it as plus c. Those two plus c's are different, but it doesn't matter because we never go back to the beginning anyway. We're always using our c as we move forward. So now we have written the function g. Let me just move this over a little so I can put g in front of this. So now we have a roadmap to get to g from f. So in order to build a power series for this function g, we're going to take our power series for f, we will integrate it, multiply it by 2, and add a constant. And we'll see that we could actually ignore this constant for now, because isn't there another constant that's going to come into play as soon as we integrate f? As soon as we integrate f, there's a constant, and so that's going to just sort of merge with that constant anyway. So now our next step is to find the power series for f. And the power series for f, we are going to start with the geometric series. So this is one of the most important power series. For the exam next Thursday, this is one of the ones you need to know. You need to know these 5. So on the 2 slides after this problem, we have 12 power series that we use super commonly. On the exam, I will pick from this group. So you want to know these ones, and we can talk about how to memorize these 5 in particular as we go through today and review on Tuesday. So the geometric series is one that we've been doing, it feels like the whole semester. It starts at 0. There's the geometric series. 1 plus x squared plus x cubed plus, blah, blah, blah. It's the one that we've been using all semester, for feels like most of the semester. And the interval of convergence for this one is -1 to 1. Okay, so what we want to do is build up and get this one for f using some basic algebra stuff. Well, the first thing I see is that we have a plus down here. So what we're going to do is take the geometric series, we're going to replace the x with -x. So all the x's are going to get replaced with -x. So if we replace x with negative x, then we're going to have 1 over 1 plus x. And in the list of power series, I call this one the alternating geometric series, because it takes the geometric series that we're familiar with, 1 plus x squared, etc., and it puts alternating signs in. So if we replace the x with negative x, still going to start at 0. This is going to introduce a switch. It will look like that. And our IOC, our interval of convergence, will be the same. That doesn't change anything. Okay, so we're getting closer. Let's go ahead and get to the x squared now. So what are we going to replace x with to turn this into an x squared down there? The x is going to become, all the x's are going to become x squareds, right? We're going to replace the x with x squared. So here, we're going to turn the x into an x squared, which means we need to turn the x into an x squared in here, in the power series. So that's going to make a power of 2k. Now, the interval of convergence, whenever we do a substitution, let's come down here to the bottom and just sort of remind you that if our IOC was -1 to 1, in other words, x had to be trapped in between -1 and 1, if we replace x with x squared, so if we take that x and turn it into an x squared, so we took all the x's and replaced them with x squareds, we'd have that. And we talked about this last class. There's a clever way to do this algebraically. You could sort of say that, oh, well, this is always true on the left, right? X squared is always bigger than -1. It's a positive or a non-negative number. So you could actually just reduce it to this. The solution to that is the same as the solution to that. And then you could take the square root of both sides because you have non-negatives. If you have non-negatives in an inequality, you can take the square root of both sides and it preserves the inequality. And the square root of 1 is 1. The square root of x squared is absolute value of x. And so we end up getting the same exact interval of convergence again. The other way I said you could think about this is to look at a graph. And if we look at the graph of y equals x squared, there's the graph of y equals x squared right there. And we want it to be, we want to know when are these x squared values between 1 and -1. So we're trying to find the x values that give us y values between -1 and 1. And we see pretty clearly that, oh, okay, if we come over here to -1 and over here to +1, we are going to have y values that are between -1 and 1. So you can think of it geometrically. We want these y values, we need to figure out the x's that give us y values between -1 and 1. Or you can use this kind of sort of offbeat algebraic technique. Doesn't matter. But bottom line is the interval of convergence, the IOC, did not change when we replaced x with x squared. So now we're here. And our last step is that we want to have an x in the numerator, so we take our power series and multiply by x to the 1. And so here we're going to multiply by x, multiply by x. So now we're going to have the power series for f. Power series. Weird. Okay, power series for f will be, when we multiply by a power of x, all we do is distribute it to the inside, and we have that. And this is one of the nice things when you multiply by a power of x, it literally does nothing to the IOC. Interval of convergence is going to be the same. So that's convenient. So now we have the power series for f. There's the power series for f right there. So what we need to do to get the power series for g is integrate it, multiply by 2. That's our goal now. So now we're back over here. So g of x will equal 2 multiplied by the integral of the power series for f, which we just created. Starts at 0. So that's k equals 0 to infinity. Negative 1 to the k. X to the 2k plus 1. And the IOC is the unit interval here, or whatever we want to call that, negative 1 to 1. And we're adding, this plus c is still on the outside here. So let me just give myself a little space, put the plus c. We're going to see that it doesn't matter, that it's going to merge with the integrals, constant of integration anyway. So that's on the outside. Okay. Now, I'm going to write the next step just to emphasize something here. We know that you can integrate a polynomial by integrating term by term. This power series is really just an exaggerated polynomial. So the integral symbol just goes to the inside. Right? It just jumps inside here. That plus c is on the outside. So we just integrate term by term. That's all it says. So then we have 2. So now we're inside the summation. We integrate. Negative 1 to the k is a constant. Anytime we integrate and there's a constant in front, the constant just floats on down. Constant doesn't do anything. It just floats on down. Doesn't matter that it's that's changing its value. Regardless of what the k is, it's just a constant. So it just comes on down. And what do? We add 1 to the power of x, so we get 2k plus 2 and divide by the new power. Bingo. So that integral has a plus c associated with it, and that c just merges with the c that's already out there, so we still just have a constant out there. Doesn't matter that it's different than the constant before, because we never go back to the previous constants. We just keep our constant moving forward. So now we're there. And we have a power series for g. So let's resolve the constant. So I think it's easy to resolve the constant if I actually write what g is equal to here, so we can kind of see, we can do a test value. So when you resolve the constant, you have to use a known point that you know, a point that you know the x and the y value for. If we plug in x equals 0 on the left, what do we end up with overall on the left if we plug in x equals 0? 0, because plug in 0, get natural log of 1, natural log of 1 is 0. So that means if we plug in 0 on the right, we also need to get 0. Otherwise, they're not equal. So let's check. When we look at this series here, what is the very first term of the series? I want to figure out whether there's a numeric constant or whether every term has an x in it. Because if every term has an x in it, they all just disappear when you plug in 0. So if we look at our very first term, which is when k is 0, oh, our first term has an x, right? Which means all terms have an x. If you plug in k equals 0 right there, you get x squared over 2. So the first term has an x. So there's no numerical constant out in front, like with our geometric series where we have 1 plus x plus, right? This series is starting with an x. So if you plug in 0 here, it all becomes 0. Right? Because there's no constants. There's no numeric constants here. So if you plug in x equals 0, this is 0. So that tells us that so when we plug in x equals 0, we get a 0 on the left. We need to get a 0 on the right. This all becomes 0 when you plug in x equals 0, which tells us the constant has to be 0. So that constant is going to be 0. So now that constant can vanish. Let's make space here. The next step is to finish this off. So therefore, g of x can be written as, now how about this 2 here? That 2 is a constant. That 2 could go into the inside if we want. And it's a reasonable thing to do here because we see that there's a 2 common in the denominator. So it's going to cancel with those 2's. Right, we have a 2 in the numerator and a pair of 2's in the denominator. It's going to cancel each one of those. Or you could think to yourself, hey, there's a 2 common in the denominator. I'm going to factor it out in the denominator, and then it will cancel with the constant in front. So you can think of it either way. So when all is said and done, we are going to have this as our new power series for g. And we have not figured out our interval of convergence yet, but that's our first big step. There's our new power series. Now, one thing I want to make sure is clear. When we do the integration, maybe you have to tweak the index. We saw that when you took the derivative of a power series, we lost a term. And if our power series that we differentiated started at k equals 0, the derivative then started at k equals 1. Right, so on Tuesday, we tested that. We said, oh gosh, okay, when we took the derivative, remember that the power on x has to be greater than or equal to 0. And we saw that when we took a derivative, if we didn't shift our index, then we had an x to the negative 1. So we always have to just double check when we differentiate or integrate that our index starts in the right place. And so we already mentioned a second ago that if we look at our first term here, let's call it a sub 0, when we plug in that 0 right there, so if we look at the term up here that we're integrating, you can look here, wherever you want to look. You're plugging in k equals 0, you're going to have an x, right? When you plug in 0 here, negative 1 to the 0 is 1. Plug in a 0 here, you get x to the 1. Plug it in here as well, it doesn't matter, you're going to get 0 and x to the 1. So that's the first term that's being integrated. So when you integrate that, you should get x squared over 2. So then we come down here, and we just want to check. If we plug in 0 here, do we get x squared over 2? So when this integrates, that integrates to x squared over 2. OK, plug in 0 here, we get a positive 1. Yes. Plug in k equals 0 there, we get x squared. Plug in 0 there, we get x squared over 2. That tells us that our index is lined up fine. That when we integrated, we don't need to shift that index in any direction. That when we plug in k equals 0 here, we can then plug in k equals 0 here, and we see that we are getting the integral of x. We're getting x squared over 2 as our first term. So that means no shifting of the index. So we're good. Now we have to test the endpoints. So now we have to test x equals neg 1. We need to know, because our series has an interval of convergence negative 1 to 1, if you differentiate or integrate, your new IOC has the same endpoints. We just don't know if we have convergence or divergence at the endpoints. Endpoints are always unpredictable. So we come down here to our series. Starts at 0. We plug in a negative 1 for the x. Can you tell me if this exponent on the x is always even? Or does it bounce back and forth between even and odd and create some sort of oscillation? This is always even, right? 2k plus 2 is always even for every k. So if you plug a negative 1 in and you have an even exponent all the time, just 1, positive 1. So we get a positive 1 over k plus 1. So there's a series. This is chapter 10 now. That's a series of numbers, no powers of x. Is it alternating or not alternating? Definitely alternating. Definitely alternating. So in this unit, in this chapter, In chapter 10, when you're asked to use the alternating series, you have to show the two steps. Here, where we're testing an endpoint, we're just going to cut to the chase with the alternating series test. And the gist of the alternating series test is, first, it has to be alternating. And then this is the A sub k. A sub k for an alternating series does not include the switch. All we need is for it to alternate, and the limit of A sub k has to be 0. Yeah. So this converges by alternating series tests, and this is all we have to write. We don't need to go through the steps. We just sort of have to think in our mind. It's either going to obviously converge because the limit of this is 0, or it's going to obviously diverge because the limit of A sub k won't be 0. So when we encounter the alternating series in this, it's going to be pretty easy. It's either converge or diverge. It'll converge as long as it's alternating if this limit is 0, and it'll diverge if that limit is not 0. So that converges. So we've gained convergence at -1. Now we're going to test the other endpoint. We're going to test +1. So +1 in for this x right here. Oh, 1 to any power is 1. So don't we end up with the exact same A sub k? So that's going to converge also by AST. So therefore, our let's get our IOC in here. So therefore, our IOC actually is the closed interval -1 to 1. We've gained convergence at both endpoints. So there is our power series for G, and there is its interval of convergence. So that type of question is definitely going to be the hardest question on the test. Look at the 2 prior exams that are up there in OneNote, and you can look at the answer key and see some more examples of finding a power series from another function with derivatives or integrals. Any questions on any of the steps there? Yeah, this section becomes a little more complicated than chapter 10 because you have so many symbols. Right? There's so much going on. It's sort of combining a whole bunch of stuff. All right, so here, let's do a couple of easier ones again. No derivatives and integrals. Those are the hard ones. We want the power series for this function f. We have a known power series. So let me point out one thing. When we look at our known power series, they are almost all centered at the origin. So when we look at these known power series, the ones are common 12, centered at the origin, centered at the origin, centered at the origin, centered at the origin, centered at 1, centered at the origin. So these are almost all centered at the origin. When we look at our second 6, centered at the origin, centered at the origin, centered at the origin, right? They're all centered at the origin all the way through. So if you're asked to find a new power series from an existing power series and the center is the origin, 99% of the time you're going to use one of these common 12 or common 11 because one of them was centered at 1. So 99% of the time if you're asked to find a series centered at the origin, which they're going to start calling a Maclaurin series. So a power series could be centered at the origin or it could be centered at some other constant. If they use the expression Maclaurin series, that just narrows down your power series to be centered at the origin. So if you're trying to find a Maclaurin series from another series, 99% of the time you just go to one of these known series and you manipulate it like we've been doing for the last couple of days. If you're told to find a power series that's not centered at the origin, then 99% of the time you're constructing it through the derivative process that we've been doing since last week. Take 4 derivatives, plug in the center, build it with that coefficient model. So if its center is the origin, usually you're manipulating a known series. If the center is not the origin, you're just doing a derivative process, doing that construction process. So let me point out a couple of other things here that are interesting. So remember that this group of 6, well, the 5, the 6th one is the binomial series, which is a little separate. But these top 5 here, they're all based on the exponential. So the exponential is the most common, most important power series for most engineers because the exponential function is so common. And the wild thing is that if you know the power series for e to the x, the power series for sine is just the odd powers with a switch thrown in. So if you know e to the x, you really know sine and cosine, because sine is just the odd powers with a switch thrown in. Cosine is just the even powers with a switch thrown in. So if you know e to the x, you really know sine and cosine. And you know that cosine is an even function, so it takes the even powers. Sine is an odd function, symmetric about the origin, and it takes the odd powers. And then if you look at sinh and cosh, they're identical to sine and cosine, except that there's no switch. So you just make everything positive. In other words, sinh and cosh really are just the odd and even powers from e to the x. So there's a lot of pattern recognition going on here that can help you to understand what the power series are and how to get them. When you look at the group that are based on the geometric series, then here, replace x with negative x. Oh, no, down here. Replace x with negative x in the geometric series to get this one. This one is just the integral of that. If you integrate both sides, you get this one. So here to here, alternating geometric. This is just the integral of that. And then natural log is just this shifted. If you turn all the x's into x minus 1, you get this one. And then arctangent, if you replace this x with x squared and then integrate, you'll get that one. Notice the powers in arctan. They're all odd. So stare at that arctan one. You see that arctan one, all odd powers. Is there any factorials in the bottom? No factorials. Let's look at sine. It's identical to sine, except you just pluck the factorials off. So arctan's power series is the same as sine's power series, except the factorials are just taken away. So there's a lot of overlap between these power series that help you to sort of keep things straight. Remember that the arctangent function is an odd function. If you look at the graph of that pen is bad. You know, arctan looks like that. It's symmetric about the origin. It's an odd function. Hence, arctan has, no, it's on the other side, has odd powers. Just like sine is an odd function, so it has odd powers. Cosine is an even function, so it has even powers. So lots of things to try to help you orient all the different types of power series, the common ones. Okay, so one other philosophical thing I want to mention for a second. When you get into differential equations and you go beyond and you're doing real life engineering type things, power series are really important for the following reason. Here's an analogy, and I've mentioned this before, if you pick a number off the number line, 99% of the time it's irrational, right? The nice numbers are the rational numbers. But when you pick a number off the number line, most of the time it's irrational. But we use rational numbers mostly when we're dealing with real world stuff. Similar analogy with functions. If you imagine the cloud of all possible functions and you pull a function out of the cloud, 99% of the time it's a power series that doesn't have a common function representation. So when you think in your mind a power series, you're imagining this polynomial that goes on forever and ever, and it's got a bunch of coefficients. in order to create a power series that's a common function, those coefficients have to be very, very, ordered. They have to be very nice. Like to get to the power series for inverse tangent or some natural log, the coefficients are all nice. There's a pattern to them. So when you just pull out a random function from the function cloud, most of the time it's a power series and the coefficients look more like an irrational number. There's no pattern to them. And so when you get into differential equations and you're taking data from the real world and you're trying to solve this, most of the time you're coming up with a power series that doesn't have a common function representation. So these are all considered Taylor series. Taylor series, if we take our function and repeatedly differentiate it, we can create these things. So to pull out a Taylor series is like pulling out a rational number off the number line. It's not going to happen. So you have this power series that doesn't represent a common function, so then you go to the remainder thing. It's like, okay, we've got this power series. We have to go far enough out in the power series to get accuracy to whatever degree. So that's why power series are so important, because most of the time when you solve a real world problem, the answer is a power series. Okay, so let's take a look at these last two. These two are easier because we just have to do some basic manipulation. We don't have to do derivatives and test endpoints. So for this one, we look at this power series here. Let's look at the closed form of it. It's a little easier. So if we take and multiply both sides by -1, then over here in the power series expression, all we did was multiply by -1, multiplying by -1. If you multiply by a constant, it does not change the interval of convergence. And remember this, we talked about this on Tuesday. If you think about the general strategy to find your IOC is to use the ratio test. And if you multiply by a constant, when you look at your a sub k plus 1 and your a sub k, they're both multiplied by the same constant, so those coefficients will cancel. So multiplying by a constant does not change your IOC. So your interval of convergence is still the same. All right, we're trying to get to this, right? We're taking this and we're trying to get to that. Excuse me. Wow. Excuse me. How do we introduce the square root? Anyone have a clever idea how we can get a square root in there? What can we do to that log to force a square root in there? You can't just replace x with something because it's more complicated than that. You have to get the square root of 1 minus x at this stage. Is there any special properties that logs have that allow us to introduce square roots? What if I multiply this by 1/2? What is the effect of that? If you have a constant in front of a log, becomes a power. Constant in front of a log becomes a power, so this becomes natural log of the square root of 1 minus x. That's what that becomes. So if we multiply the left side by 1/2, then we have to multiply the right side by 1/2. So we have this, and we're starting, this 1 right here is the initial index value. So it's still 1. And again, multiplying by a constant does not change the IOC. So we're getting there. Almost there. So we're right in here. Now we need to get this x into an x squared. That's easy. We just turn all the x's to x squared. We replace x with x squared. So if we replace x with x squared right here, then on the power series side, same thing. We're going to replace x with x squared here. And we get that. And we've seen that we have the theorem that says if you do substitution into your power series, you also do substitution into your IOC. So here is what our IOC looks like as a compound inequality. And if we replace x with x squared there, then we also replace x with x squared here in our IOC. And then here we have our geometric way. We can think of the graph. Think of the graph of x squared. We want the x values that create y values that are between -1 and 1. Or you can use the sort of cryptic algebraic method and say, oh, well, x squared is always greater than or equal to -1, so the solutions to that inequality are really the same as the solutions to that one. Right? This is always true. X squared is always greater than or equal to -1, so it's really the right side of the inequality that's important. You take the square root of both sides, and you get that. And so the IOC here, we've lost a point. The IOC here is the open interval. All right, so now we have it. That is what we were asked to do. We wanted to find the power series with the interval of convergence for that function. We now have it right there. There is our power series with its new IOC. Yeah?
If it was x to like original function, if it was x to the 2k plus like 2, for example, and you had to sub in an x squared, would that 2 be distributed?
So if you have an x to the 2k plus 2, and you replace this x with x squared, then you would have this. So the distribution would end up being 4k plus 4.
Okay.
Yeah. Correct. Any other questions on that? All right, let's deal with this one. So there's our arctan power series, no factorials. We create that arctan power series in a very similar way. If you start, oh, it's on the last slide. If you start with the geometric series, 1 over 1 minus x, first you turn it into the alternating geometric series, so you have 1 over 1 plus x. Then you replace the x with x squared, and you have 1 over 1 plus x squared, and then you integrate it, and you get arctan. All right, so there's arctan. So this is the simplest of them all. If we want to create the power series here, all we have to do is replace x with, if we want the power series for this, we're going to replace this x with 4x squared. So we come over to the power series, starting at 0, -1 to the k. That x has to get replaced with 4x squared to the 2k plus 1 over 2k plus 1. And then in the IOC, same thing. We have to replace the x with x squared. So now we have to be a little bit careful here. We have some simplification that requires some exponential function stuff or some exponential rule stuff. We can't just shove this 2 up into the exponent position yet because that 2 doesn't affect the 4. All right, so we have 2 choices. We could peel off this constant 4 and make it to the 2k plus 1. That's a possibility. And just get it away from the x. The other possibility is to write this as 2x quantity squared. And then we could combine that 2 with the exponent that's up there. Does not matter which way you go. I'm going to go that way. I'm going to write this as 2x quantity squared, and then all of that is to the 2k plus 1. And so our final form for the power series, now we can mash it together, the 2 exponents, so we could write it like this. So there we go. There's our power series. Over here, to get our IOC, we're going to divide both sides by 4. So we have this. And if we use our non-approved algebraic technique, we can say to ourselves, the solutions to this are the same as the solutions to that because x squared is never negative. It's always true. The left side's always true. And now we can take the square root of both sides. And when you take the square root of x squared, we know that the square root of x squared is the absolute value of x. So we're going to have that. And this gives us an IOC of -1/2 less than or equal to x less than or equal to 1/2. Or if you wrote it in the in the interval notation form, we would write it like that. So there is our power series for F. So when we're doing substitution, the nice thing is that we don't have to retest endpoints. So for both of these, we did some substitution stuff. We never have to retest endpoints, but we do have to substitute into the original interval of convergence and modify it based on the substitution that we use. So that is the nice way to manipulate a power series. You don't have to test endpoints. Okay, so Taylor series. So a Taylor series is a power series. A power series is just this never-ending polynomial, this exaggerated polynomial. The Taylor series is just a Taylor polynomial, which we constructed. So we construct our Taylor polynomials with this coefficient, with these derivatives evaluated at the center with these coefficients, right? That's what we do. So you construct a Taylor polynomial, you throw in dots at the end, and your Taylor polynomial is now a Taylor series. Every Taylor series is a power series, but not every power series is a Taylor series. The Taylor series has a function, a common, a known function that has this sequence of derivatives that force the coefficients to be what they need to be. A general power series, you can think of a general power series as having sort of, it's kind of like the irrational numbers where there's no pattern. The coefficients have no pattern in a general power series. So every Taylor series is a power series with nice coefficients. So for a Taylor series to be useful, we need to know two things. We need to know the values of x for which it converges. That's the interval of convergence. If the interval of convergence is just at its center, not very useful. We want an interval that's wider than the center. So this is a little bit of, this is hard. The values of x for which the Taylor series for f equals f. There's a leap of faith that we have in this class. When we build this Taylor series, Taylor polynomial, we have noticed graphically that the Taylor polynomial gets closer and closer and closer to the function as you take more and more derivatives. As you go further out in the series, it approximates the function that you started with better and better. But there is a leap to actually show that the Taylor series is equal to the original function that you started with. So when we have f equals sine of x, or e to the x, or cosine x, and we take all those derivatives and we build that series, that doesn't necessarily guarantee that the series is identically equal to the function. And that is a topic that you do in advanced calculus. We won't do it in here to prove that your Taylor series is actually equal to your function on its interval of convergence. Here we just assume that. And we've seen it when we graph the linear and then the quadratic and then the cube. You can see, so we have good empirical evidence that the Taylor series is going to equal the original function on the interval of convergence. But to prove that takes some information beyond this class. But for us, we're just going to keep that in mind, that, oh yeah, when we build our Taylor series, it's equal to our function on the interval of convergence. So here we have a function. We want to build its Taylor series. Notice the center is not 0. So all the ones that we were just dealing with, when the center is 0, aka a Maclaurin series, usually you take one of our common 12 and manipulate it, doing something. But if the center is not 0, break out the hammer and nails. We have to construct the Taylor series. And we do that with derivatives. So we just do the standard spreadsheety like thing. We're going to start with our function in an easily differentiable way. And usually what they're going to do is ask us for a collection of non-zero terms. So we want, it depends on the problem. Usually 4 is what we aim for when we're finding a power series that's, that we can't write in summation form. So if you have a power series, it has to have very nice coefficients if you're going to be able to collapse it into a summation form. If you just have a general power series, you're not going to be able to, if there's not a pattern with the coefficients, you're not going to be able to write it as a summation. It's just going to be this long expanded polynomial, and you go out as far as you can, as far as you're told. So let's go ahead and take our derivatives. If we want 4 non-zero terms, how many derivatives do we need? 3 derivatives, right? That's going to be a non-zero term, the original function, plugged in, when we plug in our center of 1. And then we need 3 more terms, so we're going to take 3 derivatives. So negative 2x to the negative 3, positive 6x to the negative 4, and then our last term, negative 24x to the negative 5. Function and its derivatives, that's column 1. Column 2, we evaluate each of these at the center. And you've gotten pretty decent at this. We've done enough of these that you have that. And now we're going to build a series, not a polynomial, so we have to be very aware. We're building a series, so we need to have that plus ... at the end. So we're just going to call this, so we're building a Taylor series. The polynomials we called p sub 3, p sub 4, whatever. We can just call it p of x since we're not figuring out a specific Taylor polynomial. We're figuring out a Taylor series, so we'll just call it p. So it's going to be an infinite polynomial. It's going to be a series. And we do the same thing that we did with the Taylor polynomials. There's 1 minus 2. Now we have to multiply by x minus the center. This term is to the first power divided by 1 factorial, if you want to write it. And then it's 6 divided by 2 factorial. So there's the 6 divided by 2 factorial, x minus 1 quantity squared. And then the last non-zero term, we're going to have negative 24 divided by 3 factorial. That there. X minus 1 to the 3. So this right here is p sub 3 of x. And then as soon as we go plus ... that's the Taylor series now. Keeping on, if you keep on keeping on with that method of derivative evaluated at the center, you build the rest of the terms. So Taylor series versus Taylor polynomial. On the exam, if you're asked for a Taylor series, make sure you put the plus ... because that's how you indicate that it goes on forever. So there is our Taylor series. Okay. Now this question asks for, so this one is going to have a pattern to the coefficients that's nice enough that we could write it in closed or summation form. So they say write it in summation notation and then determine the IOC. So this is something I will not ask you to do on the exam, to take a power series and turn it into summation notation. Typically, that is very hard, typically. Typically, it is extremely difficult to notice what the pattern in it is and to try to generalize it into a summation form. I won't ask you to do it on the exam. Let's see if we can do it here, though. Let's see if there's a way that we could rewrite this in a pretty comfortable way. So what I'm noticing is this. Usually it's not a good idea to simplify coefficients. Usually to come up with the pattern, you don't want to simplify coefficients. But notice in this case that maybe it is actually helpful. Isn't that what it simplifies to? 6 divided by 2 factorial is really 6 divided by 2, which is 3. 24 divided by 3 factorial is 24 divided by 6, which is 4. And if we went out a few more terms to really convince ourselves, what do you think the next coefficient is going to be if we simplify it?
5.
Plus 5, and the one after that? 6 minus 6. Yeah. So that pattern is going to persist with this one. So this one is not too complicated. But the function we started with was pretty simple. So, so this tells us that we can write this in summation notation, starting with 0. So k equals 0 to infinity. We definitely have a switch. We want to make sure that we make the correct terms negative. And we want that to be a k, not a k plus 1. So when it's a k, the first term is positive. So that's the switch. And then what is going to be the coefficient, and what is going to be the power of x minus 1?
X minus 1.
K for the power?
Yeah,
K for the power. So first term, that's going to go away. The second term, k will be 1. That's perfect. Third term, k is 2. So yeah, that works. And how about the coefficient? K plus 1. That's going to be the coefficient right there. Yeah. So when k is 0, we have a 1. When k is 1, we're at this term here. That coefficient will be a 2. And then when k is 2, will be a 3, etc. So that is the summation notation for this polynomial, for this Taylor series. There's our summation notation. Now, if we want to find the IOC, you need to have the summation notation in order to find the IOC because we have to use the ratio or the root test. So here we would use the probably the ratio test. So let's go ahead and do the ratio test once. So the ratio test, we are finding little r for the ratio test. That's going to be the limit as k goes to infinity, absolute a sub k plus 1 over absolute a sub k. So that'll be the limit as k goes to infinity of. So we're taking absolute values. That's going to squash the switch. No more switch. We plug in a k plus 1 for all the k's. We're going to end up with k plus 2. The absolute value still needs to be around, though, for this x minus 1 thing. So absolute value of x minus 1 to the k plus 1. So we need an absolute value for that. And then down below, a sub k, we'll have a k plus 1. And then an absolute value of x minus 1 raised to the k. So that is our ratio test. If we simplify the x minus 1s first, we see that there's one extra x minus 1 up top. There's also no k in that x minus 1, so that allows us to factor it all the way to the front. So we can say, oh, okay, x minus 1 absolute value times the limit. And this is just k plus 2 over k plus 1. No absolute value is necessary. And this limit is as k goes to infinity. What is the limit of this here? That limit is equal to 1. Polynomials with the same power, quotient of leading coefficients, divide by the highest power of k, L'Hopital's rule, 3 ways. 3 ways to calculate that. So the overall limit then is absolute x minus 1. Ratio, root, geometric series. We want to know when is that less than 1. geometric series, less than 1 converges, ratio and root test, whenever this limit that you calculate is less than 1. In general, for a power series, some of the x's cause convergence, some cause divergence. So we want to know, well, what are the x's that satisfy this? Those are the x's that are going to be in the interval of convergence. So first off, this tells us right away that the radius of convergence is 1. When you have your absolute value factor isolated, maybe you had to divide by a constant or multiply by a constant. Whatever you get, once you have the absolute value isolated, that's going to give you your radius of convergence. And so when we turn it into a compound inequality, we have this kind of thing. And if you isolate x here, you add 1 to both sides, or all sides, you have this. So this tells us that our IOC is going to have 0 as a left endpoint, 2 as a right endpoint. 1 is the center, so the radius of convergence is 1. It's 1 unit from the center to the 2, 1 unit from the center to the 0. You can take the diameter of the whole interval, divide by 2. Lots of ways to see that the radius is 1. But we don't know what our endpoints are yet. Right? We have to go back to the series and test our endpoints. Anytime we're starting from scratch to find the convergence at the end, the endpoint convergence, we have to go back and just test them. So we go to our series. We don't even care that it starts at 0. It doesn't matter. We just need convergence or divergence. We can put it there, but you don't actually need it. Because the series converges based on its tail, not where it starts. So we are looking at this series. We're replacing x with 0. So we get a -1 to the k. So -1 to the k times -1 to the k is -1 to the 2k. And -1 to the 2k is 1, because the power is always even. So those two switches combine, and we have that. Does that series converge or diverge? What was that? So it's going to diverge. Why? Because the a sub k's don't go to 0. So this is an egregious divergence because the a sub k's don't even go to 0. So this diverges by divergence test. Right? The limit of k plus 1 as k goes to infinity is infinity. Right, so it's the egregious case. And then we're going to plug in our other endpoint. So we're plugging a 2 up there. 2 minus 1 is 1. 1 to the k is just 1. So this one remains as an alternating series. How about that one? Does that one converge? Also diverges, because with an alternating series, the first part of the alternating series is the divergence test. A sub k for an alternating series is just that. You take away the switch. Limit of that is not 0. So this also diverges. And you can say either diverge by divergence test or diverge by alternating series test. Doesn't matter. The limit of a sub k is not 0. Egregious divergence. So our IOC then does not include either endpoint. So there is the last piece to the puzzle. So there's our power series, there's our IOC, and so we can say that this power series is equal to, we can think in our mind, okay, well that's equal to 1 over x squared on the interval 0 to 2. So if you graph this power series, on the interval 0 to 2, it is identically 1 over x squared on that interval of convergence. So So on the exam, I will ask you to find the radius of convergence, the interval of convergence for a power series, but I won't ask you this combination thing where you have to find the power series, figure out the closed form, and then do that. That's a lot of steps for one problem. So, and this piece right here, you can get super tangled up. This one's easy because the coefficients are pretty obvious, but so that piece we will not have on the test next week. All right, let's take a 10-minute break. Take a 10. And again, those are the 5 power series you need to know for the exam up there.
this? He's the Man vs. Wild. He's the guy. He goes out. He's like, I'm gonna survive in this wild place.
They said denominator is too powerful.
How have you not seen Bear Grylls? Man vs. Wild? That's like the okay. Well, I grew up with my grandma.
Dude, I forget that show.
Watched cable TV. And he was on. Along with River Monsters. River Monsters was also a staple. And Law and Order. Law and Order. I was watching Law and Order since I was 8. Yeah, it was pretty fire. NCIS, pretty fire. Bones. Bones, pretty fire. I thought that they got together sooner than Bones, and I was watching and I was like, yeah, they're getting together sooner. And I find out it doesn't happen until the 6th season. I was like, what do you mean? This is babe. This is baby people. You got like 20 episodes per season. They're fucking 40 minutes long. You're telling me when they get together to they've been flirting like for so long. This is crazy. That's not slow burn. That's turning off the heat and the sun cooking. Like, oh my god. I haven't reached that point because I gave up. I gave up on it. I wanted to be a forensic anthropologist for a while. But then I went to school and I did anthropology. It was really cool. But you don't make any money at all. And I would rather, make a lot of money. Because I'm very materialistic. And I'm also afraid of spending money, so I just want money in my bank account. But I don't want to spend it because I'm scared of losing money from my bank account. So I just want things that I want. I just want it on my bank account. If it stays in there, I have money, and I don't use money, then I remain rich. I've had the same $50 in my bank account for months. $50. I paid for all the college extra. I haven't
Yeah,
got a
that's
job
what I'm
because
trying
I
to
got a job.
I was looking if you do like 0%, like some C. Actually can.
Yeah, I've had the same $50 and slowly dwindling because I pay for Spotify. And I'm not giving up Spotify. Like, I've given up everything else. I'm not giving up Spotify. Need something to listen to. I need to listen to Cliff Oppenheimer soundtrack when I'm studying. Physics. That's a real necessary.
Physics and mathematics.
Oh, really?
Not back to it.
What are you guys working on? Work energy?
That was the last. No.
Have you not been in class?
No, I haven't. I can be fun. We're on chapter 12. And that's worrying about this class.
Oh, yeah. Oh, damn. Okay, we're at the same spot.
Screwed up my chapter can.
I think that we have it just even like 11. The last test was work energy and all of that stuff. So I think we started at 12. Yeah. Yeah. No.
The first one's pretty easy. I'd rather today's just 12 small short exams.
Exactly. I mean, I have learned that he does great. Really. I thought those ones, like the 70% was in the question on the test. Dude, this is ridiculous. And I was kind of looking forward to getting like a 10% because, I was sitting in taking the test and I kind of sat back and I was like, wow, I found peace. I found peace because I've never known if I was going to fail or not on the test. I know for sure. Like, for once in my life, I don't have to worry about the test because I've already failed. Like, there's no coming back from this. It's over. Like, I got 10%. And then when I got 50, I was so excited. Like, oh my god, 51. I answered 3 questions out of like 60.
Well, to me, it's the last. I like put some random bullshit that was known as the good questions. Because I didn't know. And I
easy. And this, except for angular motion, all of that stuff, anything to do with circles, I'm the worst. I'm so bad. And this entire group is circles, and more circles. I have not been paying attention. I was usually games in class, which happened in high school when I was in swimming. It might be, but see, I'm gonna make a comeback. I'm gonna make a comeback. I will get, guaranteed, I'll get 90 on this one, and then the final, I'll get 100%. Because, you know, I thought I'd get back up. What's that one? There's like a wolf shirt. There are various wolf shirts. Turned 21, my sister got me a shirt that says "Just Discussion." I wrote that out. And then I didn't get it because my license is expired.
Oh, crap, I didn't finish my water. Okay, let's see. So we did that one. All right, so let's go ahead and do the next one. And wait, has it been going this whole time? Huh, interesting. Okay, so let's do this one. And again, first thing we hope you didn't say anything weird during the break. The center is not the origin. So as soon as we see the center is not the origin, we know, break out our derivative pickaxe and start picking through the derivatives. So we want 4 non-zero terms, so we're going to find derivatives down to the third derivative of the function. Now, if we had to find the power series for sine of x centered at the origin, we'd just go over to our table of power known our common power series. But as soon as the center is not 0, just start differentiating. Be organized, treat it kind of like a spreadsheet, and your life will be fine. So we have to evaluate the function and its derivatives at the center. So sine of pi over 4, that's going to be root 2 over 2. Y prime of pi over 4, root 2 over 2. And then y double prime will be minus root 2 over 2. Y triple prime will be minus root 2 over 2. So the function and its derivatives. Our goal is to build a Taylor series, not just a Taylor polynomial. So we have to make sure we put the dots on the end. And usually I use a p for that instead of a p sub. Don't put an index on it. It's going to go forever. And we do what we normally do. When we're building a Taylor polynomial, we start with the constant. And then we add the next constant. And then we do x minus the center to the first power. So there's our tangent line, p sub 1. That, up to that point, is p sub 1. It's the tangent line. To get to the next term, we're going to go minus root 2 over 2 multiplied by 2 factorial times x minus pi fourths quantity squared. So that is now p sub 2. That's the best quadratic approximation, centered at pi over 4. All right, last term that we want, last non-zero term, we're going to put a 3 factorial in the denominator. We're going to have an x minus pi over 4 to the 3, and then a plus dot, dot, dot. So make sure we indicate that it's a series and not just a polynomial. So there is our Taylor series. And we will not find the closed form and find the radius of convergence and the interval of convergence. This is as far as I would ask you to go in the test. Any piece there that you're curious about?
You don't have to simplify the denominators. with
Don't need to
sometimes.
simplify coefficients whatsoever. If you want to, you can, but usually establishing a pattern is easier when you don't simplify them. Totally fine to leave them unsimplified. Totally fine. It's the one time in math that we don't like take off points for not simplifying. Usually everywhere we take off points, except with power series. Power series, don't need to. Yeah, kind of funny. Okay, so now here's one that's centered at the origin. If we see find a Taylor series when the center is the origin, aka a Maclaurin series, we're just going to grab one of our known power series and do what needs to be done. So here what we see is, oh, we're just going to replace all the x's with negative x. So we're going to take x and turn it into negative x. That's our strategy. So the power series for e to the negative x, if we write it in expanded form, what we see happens is that all the odd powers turn into terms that are negative. And in our summation notation, so it's easy if you're starting with summation notation, it's easy to just replace the x with whatever you need to replace it with. Okay. So replace the x with negative x. We can peel off that negative 1 to the k, kind of isolate it as a switch. And we have to do the same thing in the interval of convergence. So the original interval of convergence said that x was between negative infinity and infinity. Well, if you replace x with negative x, does that change anything? You know, multiply by negative 1, and of course you have to switch the signs, and the inequalities bounce the other way. But yeah, you still have the same interval of convergence. It's not changing anything. So this interval of convergence is negative infinity to infinity. So when the center is 0, we're just doing some sort of manipulation of a known power series. It's when the center is not 0 that we have to do the construction process. All right, you all try that one while I go fill my water bottle. Be right back. So if these substitution ones are pretty easy. Just replace the x with 3x in this case. And that's totally fine. This is another one of those things. You could do some sort of coefficient simplification a little bit. You could pull the 3 off. So it's 3 to the 2k, and then x to the 2k, and then divided by 2k factorial, 2k quantity factorial. Either way is fine, though. Doesn't really matter. So there is our power series. Let's check our IOC. So the original IOC, negative infinity to infinity, there's x. If you replace x with 3x, is that going to change anything? So we're still going to have the entire real line as our interval of convergence. So same IOC. So substituting into a known series, love it. Super easy. Super easy. Makes us happy. All right. Center not zero. Derivatives. Center not zero derivatives. So here we want to start with our function and then differentiate. And I'll write the derivative in a way that it's easy to keep on differentiating. It's usually easiest. Most of us find it easiest if you have an exponent instead of a quotient. And then we have to evaluate the function and its derivatives at the center. The center here is given to be E. So our four coefficients look like that. Plug E into each of them. And then we're going to build our Taylor series. So Taylor series. So Taylor series starts at 1, and then we add 1 eth, 1 over e. And then it's x minus the center to the 1 power. So x minus e. There's our tangent line. And then minus 1 over e squared multiplied by 2 factorial times x minus e squared. There's p sub 2. And then we keep that pattern going. So we have 2 over e cubed times 3 factorial times x minus e cubed. That's p sub 3. And to turn it into a series, we just add the ellipses at the end. And there's our Taylor series. Don't need to simplify any of those coefficients. Just leave them as they are. It's totally fine. One time in math. All right, you all try this one, number 28. So remember that, just as a reminder, when you do your derivative, this is an exponential. So the derivative is itself multiplied by the natural log of the base. So go to 4 non-zero terms. Any issues with derivatives? Say that again. But you're adding these coefficients.
I'm not there yet.
Oh, but this is a constant.
This to, yes.
So you don't have to use product. You don't have to use product rule.
Oh, okay.
So because it's a constant times 10 to the x, that constant just drifts down. So you're only needing to differentiate 10 to the x again.
Okay.
So the integral of 10 to the derivative of 10 to the x is 10 to the x ln 10. So you're going to have this, and then yeah.
Okay.
Yeah, exactly. But it's going to be ln 10 squared now, because when you differentiate this, the derivative of 10 to the x is this, but then you also have that from prior, so it's multiplication. Does everybody see these derivatives? So this ln 10 is a constant, so that ln 10 drifts down, and then when we differentiate 10 to the x, we have to then take that constant of natural log of 10 and multiply it by natural log of 10, 10 to the x. So that we bump up the power on natural log of 10 each step of the way. But we don't need a product rule because this natural log of 10 is a constant. So it just floats down. So when that comes down, then we differentiate 10 to the x, and then we have to bump the power of natural log up. And when we do our evaluation at our center, so the center here is 2. So we're going to get 100. And then here we'll get 100 multiplied by natural log of 10. Here we'll get also 100, but natural log of 10 squared. And if you want, you can use that weird strategy that this book uses and puts the 2 right on the ln. Most books do the natural log of 10 quantity squared, but you know, if you want to use that shorthand notation, they put the square right there, you can. Totally fine. And then this will be 100 natural log cubed of 10. So that gives us the function and the derivatives evaluated at the center. And then our p of x will be the first constant plus the second constant multiplied by x minus the center to the first power. So that is our tangent line. And then we add the next constant, so 100 natural log squared of 10 times the center squared, and that's all divided by 2 factorial. And of course you don't have to, but you can always think in your mind, like this is, you can see the pattern here. Right, you can think of it as starting at 0 factorial, which is 1, and 1 factorial is 1. So if you wanted to, you can kind of underscore the pattern by putting all those in. You obviously don't have to. And then our next coefficient is 100 natural log cubed of 10 divided by 3 factorial multiplied by x minus 2 cubed, and then plus dot, dot, dot. So there is our Taylor series for that function. So that is how the calculator is computing 10 raised to a power. Like if your power is some non-integer power, like if that is a power of e, it's going to use that. Multiply, divide, subtract, add. That's what it'll do. Okay, binomial coefficients. How many of you have seen Pascal's triangle? About half of you, some of you not seen it. So Pascal's triangle is a visual representation of the binomial theorem. So let's just look at where we're going, and then we'll talk about some of the details in a second. So where we're going is to look at the binomial expansion to an integer power here. So we're going to take a binomial, polynomial of 2 terms, and that's what the expansion looks like. And the coefficients are very symmetric. And the coefficients come from Pascal's triangle. That's one way that we do them. Like usually in an algebra class, you learn, oh, this is going to be x plus 1 to the 1. This is x plus 1 to the 2. This is x plus 1 to the 3. This is x plus 1 to the 4. That's x plus 1 to the 5. So those coefficients always fit this pattern of Pascal's triangle. To build Pascal's triangle, you're adding the two numbers above to get to the number below. So you add the 2 and the 1, you get the 3. 2 and 1, you get 3. 3 and 1, you get 4. 3 and 3, you get 6, etc. So you're always adding the two numbers that sit right above it. And so what we need is to come up with a mathematical representation of these coefficients. Bless you.
Thank you.
And that's what the binomial coefficients are. So let's first start with an example, because some of you have never seen this before. And if you've had a stats class, you will have seen it. So the way we pronounce this is 5 choose 2. It's called the binomial coefficient. And if you're dealing with a statistics class or doing a combinatorics within a stats or a math class, the classic example there is that, okay, we've got a bag, there's 5 balls inside the bag. How many ways can you pull 2 out at a time? What are the number of ways that you can pull 2 from 5? So that's what this is going to give us. 5 choose 2 is going to be the number of ways you can pull 2 from 5. And the mathematical definition of this is that you take the upper number, factorial it, take the lower number, factorial it. So 5 choose 2 is going to be 5 factorial divided by 2 factorial multiplied by the difference, factorial. So 5 minus 2 factorial. So that is how we compute it. If we had 9 choose 3 factorial, it would be 9 factorial over 3 factorial multiplied by 6 factorial. So upper number factorial, lower number factorial, difference. Now notice that there is this, we're moving towards this where the denominator is just the lower number factorial. And the way we get to that is as follows. Remember that 5 factorial is 5 times 4 times 3 factorial. And if I write it that way, we can cancel out the 3 factorial, and we can end up with just 5 times 4 over 2 factorial. So that's how they get rid of the factorial in this numerator here. They say start at your upper number, p, do repeated subtraction of 1, and you're going to do repeated subtraction of 1 this number of times. The lower number tells you how many factors you should end up with in the numerator. So, for example, here we're going to do 9 times 8 times 7 times 6 factorial divided by 3 factorial multiplied by 6 factorial. Here the 6 factorials are going to cancel. And we are left with 9 times 8 times 7. So we're left with 3 factors, the lower number, in the numerator, and a 3 factorial in the bottom. So if we wanted to go directly to that, if we had something like 13 choose 4, let's just cut to the chase. We're going to do 13 times 12 times 11 times 10 divided by 4 factorial. So we will do repeated subtraction of 1 that many times until we have that many factors. So repeated subtraction of 1 until we have 4 factors in the numerator. Repeated subtraction of 1 until we have 3 factors. Repeated subtraction of 1 until we have 2 factors. So that's how, the shortcut to do it without having factorials in the top and the bottom. Okay. So why might we want to do that? And this is a very common strategy in math where we have a definition of something that only holds for integers. This is only holding for positive integers, right? We can only do a 5 factorial when that's an integer. We don't know what pi factorial means. So this definition for factorial is for positive integers. But notice that right here, we no longer have in the numerator a factorial. So what this allows us to do, this generalized expression allows us to define for non-integers. Let's suppose we have e, I'm going to just call this e choose 3. We can't think of it the same way as pulling all the combination of balls out of a bag. We can't think of it that way. That's the origin of it. Bag of 5 balls, pick 2 out at a time. But this, we can define it though. The bottom number gets factorialed, and the numerator we do repeated subtraction of 1 until we have the lower number of factors, until we have 3 factors. So we can now do that. So we can take our binomial coefficient and generalize it so that the upper number, it's not a numerator, looks like a numerator, not a numerator, upper number. So that upper number with the original definition must be an integer in order to do that factorial. But when we get this modified definition, we can use irrational numbers in there. We can also use negative numbers in there. So we could say, hey, let's do -1 choose 2. Let's make that a bigger number than 2. Let's do -1 choose 4. This would be start with -1, do repeated subtraction until you have 4 factors, and then in the denominator you would have a 4 factorial. So we take and generalize the binomial coefficient definition so we can do some weird things. Why, we'll talk about in a minute. So if we look at Pascal's triangle, what we see is that, oh, each of these coefficients is really just, this is 5 choose 0, so we start with whatever our exponent is. We choose 0 things. There's only one way to take 0 things out of the bag. Right? There's only one way to not do it. Don't pull any balls out of the bag. This coefficient is 5 choose 1. This one is 5 choose 2. This one is 5 choose 3, 5 choose 4, and 5 choose 5. So you're going to notice a pattern that whenever you choose 0, it's always going to be a 1. And whenever you choose 1, it's always going to be the upper number. And so we'll keep that in mind. So another example of it. So here is how we can do a negative number. So this is just a generalization. We need to end up with 3 factors. So we start with -1, do repeated subtraction until we have 3 factors. That is that coefficient. So why might we want to do this? Okay. So first off, let's just do let's just do something like this first. So if we have a binomial, so super common, a lot of times when you see it in algebra, it's with A's and B's. So if we had to do this, obviously you know how to FOIL it out madly, that would suck. But you can just do this. This is going to be 6 choose 0. And it doesn't matter which power you start with. Normally we would say, okay, we want this to be a to the 6. And I'm going to just write the b in there, b to the 0. So there's the first term. And you know if you multiplied this all out, right, you get an a to the 6 at the beginning and a b to the 6 at the end, if you were to FOIL it all out, if you wanted to be mad. But this is how you can do it without FOILing it all out. The powers of A are just going to decrease as the powers of B increase. And the sum of the 2 powers always has to be 6. Always has to be that 6. So this is how we could do this without doing mad, oops, going down with the A's, without mad foiling. You can just evaluate each of these binomial coefficients. Six choose 6. No more A. So A will go to the 0 power, B will go to the 6th power. So that is the quick expansion of this. 6 choose 0. There's only one way to choose nothing. So this is going to end up being A to the 6. 6 choose 1. That's going to be 6. And then if we want to get 6 choose 2, we can calculate it, pretty easily. If we have oh, we didn't do the next row up here. Let's do the next row just as a thing. So this would be 1, 6, 15, 20, 15, 6, 1. So those are going to be our coefficients. So 1, 6, 15, 20. 1, 6, 15. That's going to be this one. And then 20, a cubed, b cubed, plus 15, a squared, b to the 4th. 15, now we're back to the 6, ab to the 5th. And then we're back to 1, and that's going to be b to the 6. So that's how you can expand using the binomial theorem, Pascal's triangle. Any questions on using the binomial there? Kind of cool. Gives you a quick way to do, especially like an x plus 1 cubed. We see a cubed power quite frequently, and we're kind of sloppy at it usually. But once you know these coefficients, if you're doing a cube, it's just right there. It's just that those coefficients. It's always 1, 3, 3, 1. For a cube. Okay, so now for our purposes, the binomial theorem leads us to the binomial series, which is this. It's very horrible to look at. I wouldn't bother trying to look at this general form up here. It kind of gives you a headache. Here's how I think of the binomial theorem, the binomial series. I'm going to think of, instead of writing it this way or thinking of this in my head, I'm going to write it this way. Because this way looks a heck of a lot like a geometric series. Right? This is going to be basically a geometric series with binomial coefficients instead of the 1. With a geometric series, we always have 1 as the standard geometric series where we keep doing multiplication by x. So this is a generalized geometric series. You can think of it that way, where each of the coefficients is a binomial coefficient. And this is the only way to write it. There's no numerical way to sort of simplify it and condense it other than that. You know, like you could do it like that. But there's not a way that's going to be nice and neat and tidy. Now, one thing that we cannot do in this class is calculate the intervals of convergence for different p-values. So this is always going to be given to you. The interval of convergence will be open (-1 to 1) if p is less than -1, less than or equal to -1. We're going to close off the right side if we're in this interval, and we're going to close off both sides if p is positive. That will always be given to you. We can't do the ratio or the root test on this because we don't have a simple way to simplify this. If to do the root test or the ratio test on that would be really, really hard. So we can't do that until you have some other skills. You can't do it. Okay, so determining the interval, we're not going to do it. Those are always provided. This is a nice, simple way to visualize it. Somebody says binomial series, that's what you should visualize. We don't know what the p-value is. That's going to be given to us. But if you think of it as a geometric series with weird coefficients, that is a good way to think about it. So let's do it. So first thing I have to do is identify what p is. So I've got this function, 1 plus x to the 1/2. So p is, what's p going to be here? So once again, p stands for power. So p is just whatever the exponent is, so it's going to be 1/2. So this tells us that p is 1/2. And the binomial series will say that, okay, we can rewrite this function as follows. And here's just my opinion, this is the best strategy to do it. We'll just go right through the line. There's our constant. And we're just basically writing out binomial coefficients times powers of x. So it's just the geometric series with modified coefficients. And we usually go to 4 non-zero terms, so there's the binomial expansion for this. This is how we can write powers of a binomial as an infinite series. Now you could, and great question, I can hear you thinking it, you could take the square root of x plus 1, do repeated derivatives, and plug in 0 as your center to get a so-called, well, it depends on depends on how you interpret this. But you could create a series centered at 0, or a series centered at -1, or a series centered wherever you want it to be centered by doing repeated derivatives. This one, the binomial series is going to center it at 0 if you do it this traditional way. Right? This series is centered at 0 here. But you could figure this out by centering this at 0 and just taking the derivatives and plugging in 0. And you get the same series. There's not going to be two different Maclaurin series for the same function. There's lots of ways you can find your Maclaurin series. They will all be the same. So there's our infinite series. We can't write it in any condensed way. So this, we will simplify binomial coefficients for sure. So we get rid of the parentheses here. So anytime we have a p choose k where k is 1, we always end up with p. So these two are automatic. Automatic. You choose 0, you get 1. You choose 1, you get p. So p choose k. When k is 0, you're always going to get a 1. When k is 1, you're always going to get whatever p is. Now the other two in our 4-term expansion, we have to go figure out. So let's come off to the side. 1/2 choose 2. We start with 1/2, and then we do repeated subtraction by 1 until we have 2 factors. Well, that's pretty easy. And then the denominator is 2 factorial. So this is -1/4 divided by 2. So this is -1/8. That is the binomial coefficient for this. All right. So there's p sub 2. P sub 2, the other p, not the little p here. The Taylor polynomial would be that. Taylor polynomial of degree 2. Now we need a 1/2 choose 3. 1/2 choose 3, same idea. We're going to do repeated subtraction by 1 until we have 3 factors. So repeated subtraction by 1. Subtract off 1, get a -1/2. Subtract off 1 more, get -1.5, -3/2. Then we're going to simplify this. We're going to have 3/8 in the numerator. Denominator is 6. So we're going to have 3 divided by 48, which is 1/16. There is our 4th non-zero term, plus 1/16 x cubed, plus etc. So there is our binomial series expansion for the root of 1 plus x. Okay, so there's the series expansion. So now we found, so here's the binomial series. It says use the first 4 terms to approximate. So if we wanted to approximate, can you tell me what x is going to be here? What is x going to be? So our binomial series here, the center is 0. But what is x going to be? If we want to get an approximation for 1.06, we have to come over here and say, okay, well, it's 1 plus x. That's going to be 1.06. So x is going to be 0.06. So if we want to get our approximation, so square root of 1.06, square root of 1.06 will approximately be 1 plus 1/2 times 0.06, which is 6/100ths, minus 1/8 times 6/100ths squared, plus a 16th times 6/100ths cubed. That's our approximation. So we have to identify x. So x, it's 1 plus x. So this is 1 plus 0.06. So x is being played by 0.06, which is 6/100ths. And then we can simplify this whole thing, type it all into your calculator. You know, we can do whatever we need to do. Let's not do it. If you want to type that in, you can get and see how close this actually is. But that's how we'll do it. All right, let's try another one. So 1 plus x, that's a binomial, to the negative 3. So if you wanted to, you could just start taking mad derivatives and plugging in the center. But if we're going to do it with a binomial series, it's going to be a little bit easier. We are going to say that f of x is going to equal, the p-value is negative 3, so it's going to be negative 3 choose 0, plus negative 3 choose 1 times x, plus negative 3 times, negative 3 choose 2 times x squared, plus negative 3 choose 3 times x cubed, plus etc. That is the binomial series for f. Oh, one thing I didn't say on the last thing was the interval of convergence. Let's just go back there for 1 second. So notice intervals of convergence are given to you. So with this one here, we said our p-value is 1/2. So when p is 1/2, we are over here, right? P is positive 1/2, so it's going to be negative 1 to 1 closed. So this is going to be, interval of convergence here would be negative 1 to 1 closed. And then what was the next one was negative 3. So if we look at negative 3, p is less than or equal to negative 1. So if we're at negative 3, we have the open interval. So this one here is going to be that. So that's going to be given to you. You never have to figure that out. Okay, so let's write down, they want us to have the first 4 non-zero terms. This is a series, so it's going to be 1 minus 3x. There's the first part. The tangent line is easy. If k is 1, you get p as the coefficient. If k is 0, you get 1. So now negative 3 choose 2. Let's come off to the side. Negative 3 choose 2. We start with negative 3, and we do repeated subtraction of 1 until we have 2 factors. So we're going to end up with 12 divided by 2, which is 6. So that's going to be our third coefficient here, so 6x squared. And then we're going to do a similar thing with 3. So we're going to choose 3, so we're going to have negative 3 multiplied by negative 4 multiplied by negative 5, all divided by 3 factorial. So this will be negative, negative 10? The top is going to be negative 60. The bottom is going to be 6. Negative 60 divided by 6 is negative 10. Negative 10x cubed. So there is the binomial series expansion for f. And if we want to approximate, so 1 over 1.1 cubed will be approximately equal to 1 minus 3 multiplied by, what's x going to be? X is going to be 0.1. So we look at this, so we're in the denominator. It's 1 plus x, so we look in the denominator, and that's 1 plus 1/10. So our approximation would be found by typing all this into our calculator. That'll be our approximation. I'll write down those things after class. I'll type them into Desmos and get numbers.
So for the exam, do you want
want us to approximate it, or just leave it like that?
No, you'll do it on the exam.
Okay.
I just don't want to spend time typing it. I'll type it in once class ends, and I'll write them in. Yeah, so this is, we would just type this into our calculator at that point and get whatever number we get. And and I'll say on the exam, approximate to 4 decimal places or whatever. Okay, let's try this one. So here, what is the p-value when you see that? 2/3. So our function is going to be, we're going to do 2/3 choose 0 plus 2/3 choose 1 times x plus 2/3 choose 2 times x squared plus 2/3 times, well, plus 2/3 choose 3 times x cubed. And there's our binomial series. So f will be exactly equal to that. Now p is 2/3, so we can go back and figure out our interval of convergence. When p is positive, we include the endpoints. So it's going to be -1 to 1, close the endpoint, close the interval. So f is exactly equal to that infinite series when we're on that interval. And then we want to expand it. 2/3 choose 0 is 1. 2/3 choose 1 is 2/3. So those first two are pretty quick. And then we have to figure out what 2/3 choose 2 is. So 2/3 choose 2. We start at 2/3. We subtract 1. Divide by 2 factorial and simplify. So we get -1/9. That will be this coefficient. And then we do one more, 2/3 choose 3. So we're going to do repeated subtraction in the numerator until we have 3 factors. Divide by 3 factorial. 3 times 2. Well, let's see. So we're going to end up with that 2 is going to cancel down there. The 3 is not going to cancel with anything, so it looks like 4/81 is what I'm saying. So that'll be our last non-zero coefficient that we're going to find. Bless you. So there is our binomial series expansion for 1 plus x to the 2/3. Then if we want to get an approximation for 1.02 to the 2/3, that will be approximately equal to 1 plus 2/3 times x is going to be 2/100ths. So we could write it as a 50th if we wanted. 2/100ths, doesn't matter how you write it because you're just going to type it into your calculator at this. You could write it as 0.02 also. You could definitely use a decimal in this case because we're going to be typing it into a calculator and approximate it. So it doesn't, you don't have to write. If it's easy to simplify it as a fraction, it's nice to, but this is going to get messy. We're just going to type it into a calculator. So then we're going to have 1/9, 2/3 that minus 1/9, 2/100ths squared plus 4/81 times 2/100ths cubed. So there's our approximation using 4 non-zero terms. Type that onto your calculator. Again, I'll type that into the calculator after class and we'll get a decimal approximation there. And they didn't tell us, I don't think these, I don't remember if these instructions said to approximate. Yeah, it didn't tell us a quantity to approximate to, a decimal expansion to approximate to. But. All right. So that's the binomial series. Binomial series comes into play. So on the exam, I'll tell you when to use the binomial series. should be pretty obvious. It's when you have a binomial raised to a power. Binomial raised to a power is the context. So, here's a binomial series expansion for that function. There's this interval of convergence. And this question is saying, use this Maclaurin series. So Maclaurin means it's centered at 0. Right? That's centered at 0. So use the properties of power series, substituting, factoring to find the first 4 non-zero terms of the Maclaurin series. So we want to find a series, so we should have a plus dot dot dot, but we only need 4 non-zero terms. Okay, and we want it centered at 0. So this one's a little interesting. What's your gut? If we want a Maclaurin series, any idea how we can use this to get there? Bless you. Would this build a Maclaurin series if we did this? So I know some of you are thinking this. So if you did that, if you peeled off a 3, would that build a Maclaurin series? Would that create a series centered at 0? So if we have this and we look up here, what we did was turn all the x's into x plus 3. So if we replaced all those x's with x plus 3, would that be a Maclaurin series? No, because the center would be -3? Yeah. So if you did this, so this is legitimate, this is true. Now you can certainly do this. And this is a fine way to go. So there is a series, but that is not a Maclaurin series. This series has an a value of -3. So that's not what they're asking for. Okay, so if we want a Maclaurin series, we've got to think a little bit differently. We need to force this 4 to be a 1, but we can't do it with just addition. What could we do?
Division.
So we could factor it out and use a division process. So if we factor the 4 out of the root, it becomes a 2. And we'd have 1 plus x divided by 4, right? There's no 4, so this is back like when we were doing that stuff long ago, trigonometric substitution. So we're factoring out that 4, it's going to leave an x over 4. This is going to build a Maclaurin series. So we're going to have 2 multiplied by, so there's the 2, multiplied by the square root. This is going to be 1 plus, we replace all the x's with x over 4. So this will end up being x divided by 8 minus x squared. Put that in there, we're going to have a 16. You could just write it as 4 squared in the denominator. It doesn't, either way is fine. You can simplify it or not simplify it. So 16 times 8 is 80 plus 48, so 128. Plus, when we plug it in there, we're going to have 4 cubed, so 4 times 4 cubed. So we're going to end up with 4 to the 5th, aren't we? X cubed divided by 4 to the 5th. Whatever 4 to the 5th simplifies to. Plus, etc. So that is a Maclaurin series. This series does, in fact, have a center value of 0. So that one's a Maclaurin series. So now we've written it as a Maclaurin series. How about the IOCs for these things? So for this one up here, we started with -1 is less than or equal to x is less than or equal to 1. For this one at the top, we replaced that x with x plus 3. So our interval of convergence would be -4 less than or equal to x less than or equal to -2. So for this one, the IOC is -4 inclusive, -2 inclusive. For this one, we replaced x with x over 4. So we have to do the same type of thing. We have to go to the interval of convergence. We're going to replace it with x divided by 4. Multiply both sides, or multiply through by 4. So here our IOC will be negative 4 to positive 4. So it just depends on which way you created your series. Whatever you replaced x with, you have to replace it in the interval of convergence also. How about 54? What are we going to replace x with? Negative 4x. So our series expansion, if we replace all the x's with negative 4x, so negative 4x up there is going to be 16x squared over 8 plus negative 4x there is going to, wait, this one's positive. That one's positive, that one's negative. So with the cube, we're going to replace there, we're going to get 4 times 4, which is 16 times 4 is 64. So we're going to have 64x cubed divided by 16 plus etc. And here it's simple enough. Sometimes it's super easy to simplify, then you can go ahead and do it. Not required though. So there is our binomial series expansion. We replaced x with negative 4x, so we have to come over here, take our original interval of convergence, negative 1 to 1, including endpoints, replace the x with what we replaced it with, negative 4x. Divide both the left and right sides by negative 4. Switch the inequality. So the IOC will be negative 1/4 to positive 1/4, including the endpoints. That'll be our interval. So a lot of little symbol manipulations with binomial series, but they're not very long problems, which is kind of nice. Not too long. So our final stuff, for this unit, final stuff with infinite series, it's pretty easy. This last section just says you can replace a function with its power series whenever you want. So what we're going to see in these examples, the first few examples here are simple. You could do them another way. You could just use L'Hopital's rule here. But the idea, though, is that we want to verify, we want to get a handle on the fact that we can just replace our function with a power series. Evaluate limits, find integrals, find derivatives. You can do all that stuff. So we've done it with derivatives and integrals already, but let's do it with limits. So sine, odd function. So it has the odd powers from e to the x with a switch. So we can just take the power series for sine, replace sine with it. We can divide x into each term. So x goes into x once, x goes into x cubed, x squared, all the way through. Excuse me. Man, is it spring? Spring is here. Until tomorrow. And then we're going backwards. 5 inches of snow. So now when we take the limit, all these terms at the end, the tail, they all have an x in them, and if we plug in 0, of course, they all turn to 0. So pretty, it's more kind of an observation than anything. There's not a lot of hard math going on in this section. The hardest thing is just knowing you need to know those 5 power series. You need to know those 5 series. So with this one, when we evaluate this limit using series, we're just going to replace tan x with what it's equal to as a power series. So we're going to, usually 4 non-zero terms is plenty. Sometimes even 3 is plenty. So there is arctan's power series. So the numerator has a subtraction of x. We divide everything by x cubed. And then in the numerator, if you distribute, it's not a distribution. If you combine the numerator, we have a negative x and a positive x. Combine those, the numerator loses that first term, and we're going to be left with that divided by x cubed Now we divide x cubed into each of the terms in the numerator, and we're going to be left with, let's see, negative 1/3 constant plus x squared divided by 5 minus x to the 4th divided by 7 plus etc. And this limit is as x goes to 0, not infinity. And we see that that limit is negative 1/3. Because all the other terms go to 0. The one thing we do have to be cautious of is that we're in the right interval. So our IOC for arctan is negative 1 to 1, and this limit is as x goes to 0, so that's copacetic. We couldn't take the limit as x goes to pi over 2, because pi over 2 is not in that interval. So when we use this technique of replacing a function with its power series, we just need to make sure it makes sense. We need to have the interval of convergence honored. So how about when we look at this one? We want to take the limit as x goes to infinity here. So x times sine of 1 over x. So there's x. Sine of 1 over x, we just take the power series for sine and replace all the x's with 1 over x. So this is going to be, if we want to write this out, we would, replacing all the x's with 1 over x. We have that. And you can kind of see what happens as you distribute the x. The pattern here is that you're always turning, the simplification is always ending up with a constant plus a tail that's going to go to 0. Or whatever it is. So I'm only going to go at 2 terms right here. That's fine. And here we're evaluating our limit as x goes to infinity. What's that limit going to be? 1. Because those denominators are all blowing up, which means the fractions are decreasing to 0. Because this limit is going to infinity, all these guys are going to 0. So the limit will be 1. And there is a picture of this function, the bow tie function, right there. As we're going to infinity, the limit is 1. In Calc 1, a lot of times you look at this interesting function and look at the limit as x goes to 0. The limit as x goes to 0 is 0. This is one of those indeterminate form type problems. But that's how we can do it at infinity in this case. All right, let's stop. Let's go prepare ourselves for today. The weather's over 70. Tomorrow the high is 33 or something. It's like a 40-degree temperature change. Keeps you on your toes. Keeps you on your toes. Colorado climate, gotta love it. All right, see you all on Tuesday. Tuesday we'll do review. Thursday we'll do test. Make sure a worksheet is due tonight by midnight. And make sure you know those 5 series. Start memorizing them. Get them on your note cards. Yeah?
Why are you getting rid of that first part?
This right here?
Yeah.
This x is distributing. So this x is being multiplied across. So it's x times sine of 1 over x.
Oh, okay.
So this part is sine of 1 over x. And then as we distribute that x, we get x over x, which is 1, and then x over here. Oh, I didn't cancel this out, did I?
You do.
Okay, thank you. Right. So what should this denominator power be?
X squared.
To a 2, yeah, x squared there, right. Yeah, I didn't cancel that. I saw that it didn't matter, but it does matter.
And then it's just the same thing with the previous question too.
Yes. Yeah,
So
so
you have the minus x on the outside.
so that minus x, so we're taking this infinite series and we're subtracting x off, so we're going to get cancellation right there. That x minus x is 0.
Oh, okay.
And so the only terms that are left then are these terms.
Okay.
You see it? And then this x cubed in the bottom divides into the numerator term by term. X cubed over x cubed gives us that 1. X cubed into x to the 5th gives that x cubed
Okay.
into that.
Okay.
So we're doing it all term by term.
Okay. I see.
See it?
So most of the time when you use Taylor limits, the first term's always going to usually be.
That's the one that we're sort of focusing on. It's usually going to be, if we go and use a Taylor series, it's usually that first term that's going to be non-zero in the end.
Yeah.
Yeah, and that will end up being your limit 90% of the time, 95%. Most of the time. Most of the time. See you all Tuesday.
I will be.
She'll be here. The pain is real.
Can I ask a question?
Yeah, of course.
Yeah, sir, I'm still stuck on,
Let me just
it
turn
was
on.
on that page,
Yeah.
but